Hello everyone and welcome back to the tutorial series. In this episode I'm going to show you how we can implement the Forward-Euler method, the follow integration method, and the midpoint integration method. And I'm also change a little bit here in the rigid body class. As you already can see, I removed all the integration things from the integrate method. So, I mean, you can do that too. And I'm gonna add 3 new methods in the rigid body class. And this will be the Semi-Implicit-Euler. These are the integration. Well, these are the actual integration methods. Then we will have the Forward-Euler method. And then the midpoint method. Okay, and in the next episode, I'm gonna add one method too, and that's gonna be the Ranjikuta 4 method, if I pronounced that right. First, here I'm gonna say again I want to call the semi-implicit Euler again. And the semi-implicit Euler will have, well, actually you can copy all the code from the integration part and paste it in the semi-implicit Euler, because that's the same thing. Unfortunately, I removed everything, did something else, and I can't copy it anymore, so I need to write it again. But that's now not a problem. Here I'm going to say the acceleration is equal to the scaled force with the invert mass. So the force accumulator with this dot invert mass, then the resulting velocity will be added to the current velocity. So that's the acceleration with the delta time. And then we have a delta position. And this is the velocity, the current velocity scaled with the delta time. And then we can move that shape. Alright, that's the semi-implicit Euler. Let's jump back to the browser and see if it's still working. Refresh. And there we go, it's still working. Okay. If you wonder, I changed the force in the simulation class right here. I changed it to 500. So that's why my circle will probably move a little bit slower or faster than yours. Okay. Then for the next integration method, that's going to be the Forward-Euler method. We can calculate the acceleration again with the same method like we did in the semi-implicit. Just copy this one, paste it in here. Then we're going to do something probably weird. I mean, logically, this method seems, it seems this is just right? So we're going to calculate the acceleration from the invert mass and the force. We get the velocity. From the velocity, we calculate an offset or a delta position, and then we move the shape. In the Forward-Euler method, that's a bit different, and I think it's a bit weird, because here we're gonna calculate the delta position from the current velocity. So this velocity, the delta time. And then after this, I'm gonna move that shape again. This is the delta position, and then we calculate, or we add to the velocity from the acceleration. Not the delta position, the delta time. And yeah, that's the Forward-Euler method. For the midpoint method, yeah, it's kinda it uses the Forward-Euler method too, but it takes half of it and adds half of it at the end. I'm going to show you in a second how I mean with that. First, of course, we need to say this one again, acceleration is calculated always the same. But then we're gonna calculate half of this half of the acceleration. So I'm gonna say half acceleration is equal to scale acceleration times 0.5. And then I'm gonna calculate the velocity from that. But well, yeah, from the half acceleration. So this is kind of a hybrid from the forward and the semi-implicit Euler. Here I add to the velocity, to the current velocity, half of the yeah, the velocity from the half acceleration times the delta time. There you go. Then I get again the delta position from this. So again, scale this dot velocity with the delta time. And then I'm gonna move the shape again. And then I'm gonna say, like in the Forward-Euler method, but with again half of it, this dot velocity, scale it with half acceleration and delta, not delta position, delta time. And there we go. That's the midpoint method. I can show you both of these gonna work. There you go. Let's jump back to the browser. And there you can see we add a new velocity. Yeah, this is working too. Also the Forward-Euler method. The difference between those is that the Forward-Euler method, I think, has an accuracy of 2, the midpoint method 2. Well, it also has a acceleration sorry, a accuracy level of 2, and the semi-implicit Euler has one of 3. And in the next episode, I'm going to show you how we can implement the Ranji-Kutta 4. And this will be a accuracy level of 4. Yeah, that's the best one you can use, the Ranji-Kutta 4. It's also the one with where you need the most performance. But as for my knowledge now, I think the Ranji-Kutta 4 is used more often than the semi-implicit Euler for simulations. Also in physics engines. Alright, then in the next episode I'm gonna show you how we can implement the Ranji-Kutta 4 method. See you then, have a nice day, and yeah, to the next episode. Bye.